University of Berkeley at California.
Thank you, Joanna. Hello, everyone. Today I will be talking about a project that I started with Disruptive, where we aim at manufacturing Spintronics systems on paper. And when I say paper, I mean with that really the conventional paper. So the paper we use for writing, the plant-based paper, and not the emerging paper-like materials like graphene paper or ceramic paper. So we are already on the same page. And why are we doing this? I thought, let me quote Brian Detmer, who is a contemporary artist, and we engineers are in some way also artists. And Brian, what he does is he carves books people that actually don't read anymore and throw away. So he carves sculptures out of these books. And on the picture there you see Brian, and behind him a carved sculpture made of many books. And what Brian says is, he says, I don't think the paper will ever really die. He says book, but actually book is just a collection of papers. And just like people said painting would die when photography and printmaking became everyday materials, photography really allowed painting to quit its day job and make its own story. And then he goes on and says that most of our technology, our information, our personal and cultural records are in digital form, is allowing the paper to become something new. I think it's a very exciting time for an artist like me, and it's very interesting to see what will happen with the paper in the future. So if we engineers think of the paper now as an engineering material, paper offers a wide range of technical properties that if we exploit them, we can really engineer useful devices. So paper is chemically stable. Really, if you put paper in different solvents, the paper is able to withstand these solvents. And then if we think of the electronic manufacturing that's mostly using solvents, that might be useful. Paper is mechanically bendable. So if we think of the flexible electronics that we are building, paper might be useful here. And then I went and then gathered a few quotations so to figure out the cost. And I looked at various types of paper, and then I looked at the price of a square meter of paper, and I compared it to conventional material that we are using in electronics manufacturing, like polyamide and silicon. So for one square meter of paper, you would pay around $0.1 and $2. For 1 square meter of polyamide, you would pay around $5. And for 1 square meter of silicon, you would pay around $1,000. So if really for your application paper is the material, then there is already an advantage in the material cost. Paper is an abundant resource, it's renewable, biodegradable. If you look at the pictures on the slide on the right, you see the porosity of the material. And this porosity is actually advantageous for some applications like lab-on-a-paper applications. It's lightweight, so if you need something that's lightweight, that might be useful. And if we think of the lab-on-a-paper applications that are out there, it was satisfied that the biocompatibility of the paper in the combination of biomedical substances. Now, in terms of electronics, I looked back at the last 10 years, and I picked 4 of my favorite applications that are out there. And the picture you see on the top left, that's a microscope. That's basically a microscope. It's built on a sheet of paper that you fold it and make it as a microscope. So what's the story behind that? It's a guy in Stanford, his name is and he and his students were traveling, and they discovered that the microscope that we use nowadays for medical applications are heavy, they are costly, people don't know how to use them the first time they see them, and they are expensive. And the people who need these microscopes are in countries where they don't have access to these microscopes. So how about we do it on paper? And they were able to build these microscopes with 50 cents and give them to people around the world. The second picture on the right, top right, it's a DJ deck on paper. This is Kate Jones in Cambridge, and she is developing interactive newsprints and interactive electronics on paper. The picture on the bottom left, this is Leah Buckley. She is based in MIT, and she has a different perspective than Kate Jones, where she actually wants people to make their own electronics at home. So what's the most accessible material we have at home? That's paper. So how about you build your own electronics at home? The picture on the bottom right actually doesn't have anything with electronics right now, but I see that in combination with the Internet of Things and the interconnection of objects. This is a church that's completely made out of paper tubes. This is a Japanese architect. His name is Shigeru Ban, and he builds constructions out of paper tubes. And this church was made as a substitute for Christ Church in New Zealand when it was destroyed by the earthquake in 2010. So I told you at the beginning we want to build spintronic systems on paper, and spintronics, it's the study of spin electronics, and it uses mostly magnetic materials. So how about magnetics and paper? What's already out there? What has been done? If you just think of the routine every day, if you park your car, the parking garage ticket, it has a magnetic stripe on the back of it. If you use public transportation, the subway ticket, it has a magnetic stripe on the back of it. I don't see that anymore, but the old boarding passes that we used to take to enter the airplane had also magnetic stripes on the back of them. So you see, magnetics and paper, it's a classical. We have been using this for a long time. And nowadays in research also, the manufacturing of actuated valves in laminate paper to control the flow of fluids within a paper, also different arts of actuators. How are these magnetic papers manufactured? You can manufacture the magnetic stripes by printing them or by laminating the magnetic stripe. You can also manufacture the magnetic paper during the synthesis process of paper by incorporating some magnetic particles that fill the porosity of the paper, or when the paper is already manufactured, you can dip coat the paper in a magnetic suspension. So the nanoparticles that are in the suspension, they are sucked by the paper and they fill the pores of the paper. So far, in all these applications, most of the magnetic material that were used are non-metal, mostly iron oxide, which is a hard magnetic material. And what so far has been achieved is the writing and reading of bits. So, for example, in the magnetic stripes, the papers that are filled with magnetic particles exhibit a superparametric behavior, which was expected. So, what do you want to do differently? We took the paper in the lab, and then we wanted to see what can we do actually with the paper. And what we were able to see, which was astonishing, we are able to adapt most of the technology or the techniques we use for the classical electronic manufacturing, like thin film technology, clean room microprocesses, and packaging technology. We are able to do that on paper. And I picked just two examples, the top two pictures. You see the mouse here. So on the left, this is a result of a photolithography. So you can actually do a lithography process and develop the resist on the paper. And on the other picture here, these are two wire bonds that are bonded on a copper layer that was electroplated on paper. So this really opens up a huge opportunity for using the paper and not making just a simple stripe or filling the paper randomly, but actually manufacturing a more detailed and a more complicated system. So that's what we took. And then we said, actually, we want to make systems for sensing and actuating applications. And we want to take the paper and coat it the classical way we do it in electronic manufacturing. And we want to pattern these thin films, and we want to make systems out of that. So the questions we wanted to answer are we able to actually realize some magneto-resistive effects, the ones that are actually the basis of these spintronic systems. Anisotropic magneto-resistance, giant magneto-resistance, tunnel magneto-resistance. So are we able to do that on paper? And actually when we said that, many people laughed at us and said, what are you doing? We are doing this on silicon and we are doing on these highly polished substrate, rigid substrate that costs so much. Why are you going to do it on paper? But we wanted to try it out. And the focus of today's talk is the anisotropic magneto-resistance, and we wanted to investigate that using permalloy, which is a conventional material that is used for these type of magneto-resistive effects. So I want to get you all, I don't know what's your background, so I'm just going to briefly explain anisotropic magneto-resistance. Anisotropic magneto-resistance was discovered by William Thomson in 1856. What he took is he took a bar of iron and then he measured the resistance. And then he applied the magnetic force on that iron bar and he looked at the resistance of the material. So when the electric current was in the same direction with the magnetic force, what he measured basically an increase in the resistance of the iron bar. And then he applied the magnetic force in the vertical, perpendicular to the electric current, and what he saw basically the resistance decreased. So that's his discovery. And years later, people basically deep dive into this topic and they understood the physics behind it. And the physics behind this phenomenon is basically an interplay of the magnetization of the material and the spin orbit of the electrons that scatter in the material. And people basically studied all of the transfer characteristics, not only for the 0 degree and 90-degree angle, but for all various angles. And this is actually what we are using nowadays for angle sensing. So your iPhone, when you're tilting it, it actually has an AMR sensor, an anisotropic magneto-resistance sensor in it. So I want you to look at these characteristics and then remember them because I'm gonna come back to them later. So magnetic phenomena. It's mostly gonna be an interplay with the paper surface. Now you see the pictures there. That's the surface of a conventional paper. And I like to classify the properties of the paper in 4 categories. First one is the inter-roughness. What I call is basically network topology. You have fibers that spread and connect with each other. And then you have the gaps between the fibers. That's the interporosity. And then if you zoom into one fiber, the picture on the bottom here, you see an intra-roughness and intraporosity. So for a ferromagnetic material, when it's being magnetized, it forms the magnetic domains that basically become larger and then they fuse with each other. And at the boundary of these magnetic domains are domain walls. And these domain walls, we expect them to form where the fibers meet and change orientation. It is known that the network topology facilitates the motion of the domain walls. And it is also known that the roughness induces spinning of domain walls. So you have basically an interplay of 2 contrasting phenomena that are intrinsic to the paper surface. I like to look at each fiber and then think of it as a distinct electrical conductor and a distinct magnetoresistor. And maybe, we don't know for sure, but maybe that the asperities, that these small roughnesses on the paper, if the conditions are well done and if the pores are small enough, we might have some tunneling through at the asperities of the paper, through the pores. So how did we maybe try to solve this problem? We sputtered deposit a 70 nanometer permalloy, which is an alloy of nickel and iron, which exhibits the anisotropic magnetoresistance. Sputtered deposition is a dry, solvent-free. We used a low power, so low temperature, low stress process. We wanted to eliminate basically all of the interfering factors that might affect our system. And we confirmed with electron dispersive X-ray spectroscopy that really we do have permalloy on paper. So the permalloy didn't interact or interfere or react with the paper. We cut the paper prior to coating. We used clean room paper. which has a grammage of 80, a roughness of 2.8 microns, 23% surface porosity, and the fibers were latex impregnated. As reference substrate materials, we use fused silica, which is glass, has a conventional surface quality that we use in electronics. And in order to separate the impact of the material from the surface, we replicated the paper surface into a stiff epoxy resin. So we have three systems that we compare. We characterize the permalloy coating, basically on magnetic behavior, and we used a 4-point measurement setup to track the electrical resistance and see if we get the anisotropic magneto-resistance effect in these paper systems. So using a vibrating sample magnetometry, what is that? You basically apply a sinusoidal vibration on a sample, on a coated sample, and then you apply a magnetic field, and then you can measure the magnetization. And with that, you get a curve, the curve you see here on the bottom, which gives you the magnetization as a function of the magnetic field. And what we have seen is basically the epoxy system gives a similar response as the paper system, as expected. So mostly the paper topology has a higher impact on the magnetic behavior. And what we have seen compared to this fused silica system, so the glass system, the paper system exhibits a larger coercivity. What does it mean? It means you need a larger magnetic field to demagnetize the material, and less remnants, meaning you have less remnant magnetization in the paper system. With the magneto-optical Kerr effect spectroscopy, what we were able to see here, here I have a video here on the left. It's not playing, and I don't have much time, so I'm not going to play it. But what we have seen is basically, I hope you can see that, a contrast of white to black. And the white is an indication for scattering. And what does that mean? Basically, you have electrons that's scattering. And that's happening, if you look maybe in detail, it's happening at the locations where the fibers may be bent or change orientation. So that's also another information we have gained from the characterization. Now to the magneto-resistance measurements. So we looked at the two configurations that William Thomson looked at, which are electric current parallel to the magnetic field and electric current perpendicular to the magnetic field. And what we have seen is basically the fused silica system. This is the measurement curve. On the left is the theoretical curve. You see they are similar. So this is basically the classical response that we know. We obtained it. Now comparing the epoxy and paper systems to the theoretical curve, we have obtained actually the characteristic that, if you remember from the beginning, I showed you the 45-degree angle characteristic. So the paper system at this configuration of electric current to magnetic field exhibits a 45-degree angle sensitivity. Looking at the other configuration where the electric current is perpendicular to the magnetic field, fused silica exhibit exactly what we know from theory and from ancient physics. Now, the epoxy and paper systems exhibit again the plus minus 45-degree angle sensitivity. Why is this happening? So if we look at the paper or the fiber, so if you induce current on the fiber, I mean the figure earlier, if you look here, I mean it's easy for me to tell in a system that's predictable that the current is flowing this way. Yet if I am I'm applying current on a paper, the current is flowing along the fiber. And now I have the two configurations that are the directions of the magnetic field. So each fiber exhibits a different response. Each fiber has a different angle. So the angle is not given. It's basically given just by the fiber. I'm not giving it to the system. And then I have a stochastic orientation of the fibers. So the question is, that's what we are trying to solve and understand right now. How is the superposition of these individual fiber responses interacted with each other, and explain the experimental result that we have obtained? Now, in summary, I would say that what we were able to see that the surface topology of paper has the highest impact on the magneto-resistive behavior. When we compared the paper system to the fused silica system, we have obtained a larger coercivity and less remnants. We were able to see where the domain walls of magnetization form, and they form mostly at the bending location of the fibers. From the two measurement configurations we have done, we have seen that the sensitivity of the magnetic paper systems gives us a 45-degree angle sensitivity. And we are currently continuing our experimental work and computational modeling to understand why this is happening. And we would like to investigate in the future and report on that maybe at next ECTC on the performance of these systems if we use nanopaper instead of micropaper. The paper that I've used in this work has fibers in the microscale. So if we go to nanoscale, what will happen? The thickness of the coating, how does it affect the performance of the system? If I pattern the coating, how does the performance change? And the paper flexibility, when I bend it, how does it change the performance of the magnetic system? So I'm at the end of my talk, and I would like to thank the German Research Foundation who funded this trip to San Diego. Rudolf Schäfer and Stefan Pofal, who assisted us in the magneto-optical measurements, Meriem Akin for the noise measurements, and my colleagues at the Institute of Microproduction Technology for helpful discussions. And I would like to thank you for attending this talk, and I would like to take any questions that you might have. Thank you.
Any questions?
Have you considered coating the paper prior to the metal deposition to reduce the impact of the fiber?
Meriem, sir, can you just repeat?
Yes, I will repeat the question. The question was, have you considered coating the paper to cover the roughness of the paper and then do the magnetic coating? Our approach is to use the paper the way it is intrinsically and then keep actually the structure of the paper the way it is and see if that has a benefit on the magnetic performance.
Yeah, my question would be, I guess this is very good, but the only one drawing back is a moisture. Okay, if your device is a very wet environment, like in South Asia, and then you get trouble with this.
Yes. So the question was, the drawback might be the moisture intake of the paper. Yes, that's true. Paper likes moisture and it takes humidity. So that's also maybe in the vision. How long do you want to use this paper system for? So it's a low-cost system. Low-cost system, maybe you can live with using it a couple of times. Or, I don't know, we haven't looked at, we are at the very beginning of this roadmap. So reliability will be a focus when we understand the physics.
I was wondering how, when you measure the magneto-resistance, how you enter your paper, because when you apply magnetic field, every paper by minute, my paper is magnetic stored, or microscopic scale, the fiber might move and cause the noise.
So the question is, how are you fixing your paper in the magnetic field? Because the paper is lightweight, and then if you apply a magnetic field, the magnetic field applies some kind of vibration, and you might see a local vibration in the fiber. A very good question. And we have looked into that actually. I have done some microscopy in the magnetic field. So macroscopically or microscopically, we are not seeing any change in the zoom while the paper is in the magnetic field. If this is happening in nanoscale, I am not able to answer that question. So that's also another important point. But if that's the case, we have to live with it. Maybe there is some little noise that we can maybe filter computationally. Yeah.
How repeatable is the structure of paper? Like, do you see a lot of variation piece to piece?
Yes. So the question is, how repeatable is the structure or the surface of the paper? Sure. It's not, you will never get the same response from one paper to the other. The fibers, they are stochastically synthesized. So in mechanics or in magnetoelectronics, if you have the representative area element, that's what we call it. So if you go in smaller size, sure, you will never get the same answer. But at a certain size, the variation will not be as high. So you will not have the same response for each system, but the variation will be less.